Good morning, everyone. Today we come to lecture 16. Okay. On the introductory Raman Spectroscopy. Okay, so the content, most of the content into this lecture comes from this book. Okay. Introductory Raman Spectroscopy. So by this author. Well, this day is very early. Okay, you can get this book in the library, and it's also available online. I mainly talk about the I think it's the first chapter, the basic theory. Like if you click it, then you see it's chapter 1, the basic theory. Okay, so let's start with something simple. Okay, with something simple. Let's consider that you have a molecule. What kind of molecule should I start with? Let's say just a oxygen molecule then. Okay, oxygen. You have 2 oxygen. Okay, or any kind of molecule. Okay, so there will be a electron cloud. Okay, there will be an electron cloud surrounding it. Then you maybe let me rotate it. Okay, that will kind of look better. Okay, then you shine the light on it. Okay, you shine the light. Okay, so you shine the light. So you have the electric field. The electric field will have E0 cosine omega t. Okay, so a very simple configuration. So once you shine on it, you are going to move the electrons around inside it. So if you apply an electric field here, let's consider electric field here. Then certainly the electric field will push the electron on one end. You have there's some electron here and some charge here. Okay, some electron, just some charge here. Some, let's just say delta minus. You only move it slightly. Okay. So then you will induce a dipole. You induce a dipole. Okay. So the relationship between them is this. P will equal to alpha times E. Okay. I mean, you can add a vector here if you like. Okay. So generally, this alpha is the polarizability tensor. So generally, alpha is a symmetric matrix or tensor, if you like. Okay. Alpha yx yz zx zy. Okay. It is a symmetric. Is a symmetric tensor. Okay. So now let's consider vibration. By the way, once you get the dipole, the dipole moment, then the dipole will just oscillate, and then we will radiate the light. Okay. So once you get the dipole, then the radiation will be straightforward. Okay, let's consider vibration. Okay, and the vibration we use we use this Q to represent the vibration, equal to Q0. This vibration will be the time. And then it will be cosine. Okay, so here, this is the vibration frequency. So this is the normal mode displacement of the normal mode, and this will be the magnitude. So once you get the normal mode by solving the dynamic equations, so usually the normal mode will only have just one variable there. That is the displacement. Okay, it may not be a simple x or y vector. It may be it's a combination of many things, but eventually you can use just one displacement to represent the normal mode. Okay, and it's vibrating like this. Okay, so then this polarizability tensor would depend on this, because a vibrating molecule will have slightly different polarizability tensor. Okay, so this alpha. Okay, so let's alpha 0 be the polarizability tensor when there is no vibration. Okay, this is the original one, when the molecule does not vibrate at all. Okay, so once you, and then let this be the polarization when there is when there's vibration, QT. Okay, so this will be a time dependent. Okay, this will be time dependent. Okay, so now the vibration is usually very small. The magnitude is usually very small. Okay, so you can use a Taylor expansion. It will be this. Will be this plus this dq, and q equal to 0. Okay, when there's no vibration, and then you times q. Okay, so of course you can have more. Just keep going on, but we're not going to investigate. Those are higher order. Okay, so let's continue. So let's plug it in. Let's get this thing. Copy. So you can plug it in this one. Okay. For simplicity, I simply write a 0 here. Okay. Just simply write a 0 here. Q. And times what is the electric field? Electric field is this one. Okay. Okay, so, and then you continue. But this time we're going to put this in. Wait. I think I can just put this here. Okay, this is the first term. This is the second term. Okay, then copy this one more time. So then we're going to plug this in. We're going to plug this in. What is Q? Q is this thing. Copy. Okay, something like that. Okay, just Taylor expansion, nothing very special. And then, of course, you can slightly change the order. This thing will be Q, and then you have a cosine omega t, cosine big omega t. So this thing will be 1/2 t plus cosine minus t. Okay, so eventually you get a result like this. And then plus 1/2 this thing. And then Q0 E, and there's some space, and then this thing. Okay, so this is the mathematics. Okay, so now look at this equation. Look at this equation. You have more than one frequency now. So this one has the same frequency. So we call this the elastic scattering. Or you call it the Rayleigh scattering. Rayleigh scattering. And this one is a different frequency. So we call it inelastic. Or you can simply call it Raman. Or Raman scattering. Raman scattering. Okay, so these two terms has their names. This term. This term is called the anti-Stokes Raman scattering. Corresponds to the anti-Stokes Raman. And then the same thing. This minus corresponds to the Stokes scattering. Okay, so you have two terms. Stokes is the last name of a person. Raman is the last name of another person. Okay. I think Stokes, the name was first. I just explain a little bit about the history. So what do you mean Stokes? So historically, people measure the photoluminescence before Raman. Okay, so Raman was I think the Nobel Prize of Raman is 1928, if I remember correctly. Okay, it was important because it actually is a certain manifestation of quantum mechanics. Okay, and I think this is the first Nobel Prize for India. Okay, I once asked the student the question, why was Raman scattering discovered in India, not in Europe, not in any other places? Do you know that why?
I remember.
Yeah, it's an interesting story. Okay, the reason is because at that time, because laser was discovered in 1960s. Okay, around 1960s. I mean, nowadays when you do Raman, it's so simple. You shine the laser, measure, you see a Raman peak. It's so simple. But in the old time, it's very non-trivial. Because in order to do the Raman, you need to have a strong single frequency laser. Strong single frequency light source to do it. And at that time, there's no laser. And I don't think the white light lamps are like a very strong either. So you have this limitation in the experimental conditions. And the advantage of being in India is that they have the sunlight. Okay, they have a strong sun there. Okay, so Raman just used the sunlight. So he used the sun. Okay, the sun, and then you have some sunlight go in. Then basically the experiment was something like you use a prism, diverge it. Okay, and then you add a slit here. Then you have a single frequency light, and then I think his spectrometer is a black room. Okay, you go to a black room. Okay, and then you have the grating, and then you shine the light. Of course, there's a sample here. Then you just analyze the spectrum. I think he used some film. Those films that you take pictures with the old style camera, and then you see besides this Rayleigh scattering term, he also see both of the Stokes and anti-Stokes term, the lines, and he find that if you change the sample, you change the position of those lines. Those lines behave like a fingerprint of the materials, and then he find this is very useful because for some of the solution, they look exactly the same if you look at it by your eyes. When you do Raman, you can identify very accurately. And he at that time he took a big effort to promote his method in Europe to make people know it. And fundamentally, this is a quantum effect because I mean you can use quantum mechanics to explain it. Okay, but the method is so powerful because it is so useful. Okay, so why is it called Stokes? Why is it called Stokes? Stokes is another name when those people they study PL. They find that every time you shine the light with a frequency on it, you receive a PL that with a frequency smaller than this original frequency. I think Stokes contribute to this work. Okay, so this kind of shift, you can say it is called the Stokes shift. So basically, Stokes shift means it is lower in frequency, and I think the original the origin just comes from the PL study. I'm not sure it is called Stokes shift or not, but nowadays if you say Stokes shift, then it basically means redshift. Okay, so because this Raman line occurs in a lower frequency, is called the Stokes Raman scattering, and then this is a higher frequency, then it's called anti-Stokes Raman. Okay, so that is the reason for those terminologies. Is okay. So you can see that you can kind of explain all this by using a simple Taylor expansion. Okay, and if you want to go high order, then you simply do it for one more. If you want to go higher order, you only need to do this twice, and then you have the Q square. Then you put in you put in this twice, then you're going to have the overtone of the Raman peak. Okay, so just like that. Okay, so now let's see what decide whether a phonon mode is Raman active or not. It's completely decided by this thing. By this thing. If this is 0, then it's not Raman active. If this is non-zero, it's Raman active. Okay, so let's write it down. Okay, if for a fraction mode, it is Raman active. Okay, it is Raman active. It's okay. So this is a tensor. This is a tensor. Yeah. So this is a tensor. Why? Because alpha is a tensor. So the Raman tensor will basically be this thing. Okay, you just need to do the derivative on all of them. Copy. So you just need to do derivative. Of course, eventually you need to set this to be 0. So this is the tensor that decide whether it is Raman active or not. Okay. I mean, you can call this a Raman tensor. Okay. Yeah. So this is Raman tensor. And first, this is a symmetric tensor with only 6 independent elements. With only 6 independent elements. Of course, you have 6 independent elements. You can say some of the elements can be 0. Some of them are not 0. Okay, so when you say Raman mode is Raman active, it only means it is at least one is not 0. Okay, but there will be some particular form of the Raman tensor that you can use the light with different polarization to probe different elements in the Raman tensor. Okay. But generally, when you say a mode is Raman active, it means at least one of the elements is not 0. But when you say it's Raman inactive, that means all of them are 0. Okay. So in complementary, let me talk about also the infrared interaction. So we talk both of them together. Okay. So for infrared, you have a molecule, let's say a CO, okay? Let's say a carbon monoxide. Then there will be some charge. There will be some charge transfer. I suppose maybe carbon will take more electron. Let's assume so, okay? So we take a little bit electron. So there will be some dipole. So there will be a dipole P. Okay. So if we need to know the oscillating dipole. Emit light. Okay, when you have a dipole oscillating, emit light. Okay. So also absorption of light. I mean, if you get emit light, it will also absorb light. Okay, requires oscillating dipole. Or oscillation of dipole. Okay, oscillation of dipole. So if the dipole is oscillating for vibration, it is infrared active. If you have a dipole, and when it vibrates, the dipole is also vibrating, then it is called infrared active. That means it can interact with the light, it can emit light, it can also absorb light. Is that okay? Okay, so now with this criteria, we can decide whether a mole is Raman active or not. So let's start with something simple. By the way, this Raman tensor, you can use an ellipsoid to represent it. The ellipsoid, for example, I mean, for all kind of this tensor, you can use an ellipsoid to represent it. Basically, you use an ellipsoid to represent it, and then okay. So on one direction, on different direction, you have different value. Okay. So this is one. This is another one. This is another one. So this value, usually for Raman tensor, we plot in this way. We plot it in 1 over alpha square. So this is, let's say this is x, y, z. Then this value will correspond to 1 over alpha y, 1 over alpha z, 1 over alpha x. So these are called the principal value of this 1 over alpha square tensor, because you can always diagonalize the matrix into a diagonal position. So you diagonalize it. You diagonalize it. Okay. You change the coordinate so that you obtain a diagonal form of the matrix. Then you define these two. But what about if you go to another direction? Then you pick this value. You pick this value. Okay. So this is a kind of a typical way to represent a matrix by using a geometry object. Okay. You use one ellipse, you represent a tensor. Okay. So this is just like some graphical way to represent a tensor. Just like you use an arrow, you represent a vector. You use the ellipsoid, you represent a tensor. Okay. So we're going to use this graphical way to represent the change of the tensor. Okay, so let's start with something simple. Let's start with the CO, with the carbon dioxide example. Okay, carbon dioxide. So let's consider that there are 3 vibrational modes of carbon dioxide. Okay, so the carbon dioxide has a form like this. Okay, C with 2 O on the 2. It's a symmetric. Molecule. So this is when there's no vibration. Okay, so now let's say you vibrate. If you want to represent the ellipsoid, you just use something like this to represent it. Okay, so this is the ellipsoid. Okay, use an ellipsoid. It should be symmetric. Let me symmetric. Yeah, some Okay, now it looks more symmetric. Okay, so now let's say you contract mole 1, mole V1. So then you contract. Okay, so once you contract, then you have the same thing, and then you just shrink it. Sorry, make it bigger. Make it bigger. Why is it bigger? Because when it's shrink, the polarizability is actually larger. Let me see. Wait. Sorry. We not larger. Because we're using 1 over here. Okay. So when it's shrink, the polarizer, this ellipsoid will get bigger. Okay, but it doesn't matter. It doesn't really matter. Okay. Okay, then on the other end, you get bigger. Get bigger. Okay, so this thing will shrink. Okay, so you see that the ellipsoid is changing. Then what do you get? Okay, now you plot. You plot alpha as a function of Q. So at the beginning, Q is equal to 0. You have a certain value here. You have a certain value here. Then here you get bigger, get smaller. Okay, so you just go like this. Just go like this, get smaller. So if you do it continuously, you expect to get something like this. So what happened on the two end doesn't matter. Okay, what matters is that here, this slope is not 0. Okay, so this mole is Raman active. Is it okay? Is it okay? Not difficult, right? Okay, this mole is Raman active.
So the y-axis means that when you take one and
which y-axis? Yeah, of course. Yeah, you take one element, but I mean you can see that all the element changes, right? Because the whole molecule get bigger, every element is changed. Okay, so now let's consider another mole. Let me move this away. Okay, let me just move this away. Okay, there are totally 3 modes. So let's consider a different mode. Let's consider V2, mode 2. The mode 2 will be C. Of course, the middle one is always the same. We just copy this. So this one will be go to like this. Go like this. So like this. Okay. So it move like this. Okay. So then the whole thing will get bigger. Okay. The whole thing will get bigger. I mean, it may not be like this. I just copy for simplicity. Okay. So then on the other end, all you need to do is to flip it. Okay. I see. Okay. So this is another direction. Okay. So just like this. Okay. And then this one will have just the same ellipsoid. It will be just the same. I mean, you can observe it, right? This one and this one, they just look the same. Okay. So when you apply electric field here and here, you just induce the same dipole. You just induce the same dipole because the electric field is oscillating back and forth. So the electric field see this one and see this one, they just produces exactly the same thing. It's okay. So the Raman tensor, the ellipsoid is also the same. Okay. So when you do maybe I where should I put it? Okay, like this one then. Okay. Okay, so this one, if you want to make a plot, let me copy this. Then what you see is just you will see both ends are the same. Because to these two, if you connect it, they must go smoothly. Because both sides are the same. No matter whether they go up or lower, they always have a flat slope. So this mode is inactive. Okay, or you can call it Raman forbidden. Okay, so from this you see the first mode is Raman active, the second mode is Raman inactive. Is it okay? Then let's go to the third one. The third one is V3. Of course, the middle one is always the same. Copy. The third mode is a bending mode. Is a bending mode. It bend like this. Okay, basically like this, like flying. Okay, bending mode. And then this tensor will certainly look different. The tensor ellipsoid will look something like this. Let me make it bigger. Okay. You can see the shape like this. The more symmetric the molecule is, the more like a sphere it is. The more asymmetric it is, the more it looks like an ellipsoid. Okay, so this is very anisotropic. So usually the longer end here will produce a shorter length in the ellipsoid. Because when you apply the electric field, the electron are easy to move in this direction. If you apply the electric field here, the electron are confined here. Okay, so the polarizability is different. But if you make it like this, then it's more like a ball. You apply the electric field here and here, the difference is already smaller. Because why? Because you're basically picking different component of this bond. When the bond is tilted, then it's more similar to each other. Okay, of course here I'm kind of exaggerating. It won't bend that much. Okay, but you can expect it will become more like a sphere when it is bending. Okay, so similarly, when it bends in another way, then it's more like a sphere on the other side as well. Okay, so these two will be the same. Then eventually, you get just the same thing here. You just get the same thing here. So this mode is also Raman inactive. Yeah. Okay, so in summary, in carbon dioxide, there are 3 modes. One of them is Raman active. This one is Raman active. And this one is not Raman active. This one is not Raman active. Okay, so using our simple theory, then we show that. You don't actually need group theory. And I actually personally like this kind of pictorial way to understand Raman, because it's more straightforward, more visually appealing. Okay, so now let's consider the infrared activity, the infrared. Okay, so okay, let's consider the first mode. Let's just copy. Okay. So let's consider the first mode. Okay, what is the dipole? Carbon will, I will say the carbon will take some positive charge here. No, negative charge, I think, because carbon is a smaller atom. Oxygen is a bigger atom, so I suppose the electron will tend to flow to carbon. Then this one will pick up some positive charge. Positive charge, positive charge. So what is the dipole? The dipole is 0. Okay, and you have just the same thing here. Actually, it doesn't matter how much they oscillate. The dipole is always 0 because it's symmetric. Okay, it doesn't matter how far away. Of course, this delta and this delta, they will be somewhat different. Okay, because once you change the molecule, the amount of electron transfer will slightly be different. So let me say this. Anyway, delta just means small. Okay, it doesn't matter. Okay, here you have delta minus delta plus delta plus. So this P is also 0. Okay, so there's no dipole oscillation. Okay, no change of dipole. Okay, that means it is infrared inactive. Is that okay? Okay, now let's go to the second mode. The second mode is this one, this guy. Second mode. So this one is delta minus delta plus. Okay, now, so this one, the P is 0. This one, you can see that you have more negative charge here, right? I think more accurately, you should use, you have more negative charge here. And so the dipole will go like this. The dipole will go like this. Okay. Is it? The dipole go from negative to positive? Or positive to negative? Okay. So this way. Okay. So you can say P larger than 0. Okay. Then P is smaller than 0. Okay. So the dipole is oscillating. When it vibrated, the dipole just go up and down, up and down. Okay. So there's a there is change of dipole. So that means this is infrared active. Okay, so we're done with this one. So let's go to this one. Let's go to the third one. So we draw the same thing. Then here you have this. So what is the dipole? The dipole is going up, right? Going up. So this P is 0. And then this is going down. So the P is like this. Okay, so the dipole going like this. The dipole is oscillating. That means they're infraactive. They're infraactive. Okay, so in summary, you have V1, V2, V3 mode. So Raman active and infrared active. Okay, for mode 1. For mode 1, let's review. Sorry, I keep going up and down. For mode 1 is Raman active. Okay. And mode 2 is Raman inactive. Raman inactive. No, Raman inactive. Okay, so you can just fill it in here. Yes. No. No. So for the infrared, this one is infrared inactive, infrared inactive, and then infrared active, infrared active. So this is no, yes, yes. So this is how we judge whether you can probe them with the Raman active or not. So now, if you come to design an experiment to study the vibrational modes in carbon dioxide, then you need to use this table. If I want to study this mode, you should use Raman spectroscopy, not infrared. If you want to measure this tool, then you use infrared, not Raman. Okay, and this is not a coincidence that you see that they are complementary. As I told you before, if a certain system has inversion symmetry, then the Raman activity and infrared activity, they are always opposite each other. If a mode is Raman active, it is not Raman inactive. So let me write this for system with inversion symmetry. The Raman and IR active modes are different. Are always different. And they are opposite to each other. And if you have a system that has no inversion symmetry, then some of the mode can be both Raman active and infrared active. So let me give you a common example. For example, another example is water. Water has a relatively low symmetry because the molecule is bended. Not like a carbon dioxide. Carbon dioxide is straight, but water molecule intrinsically is bended. Okay, so it's already like this. Okay, it's already like this. So let's go through water molecule because we already have the example of carbon dioxide. So water molecule, this part we can go faster. Okay, we can go faster. So the first mode is mode 1. Mode 1 is a stretching mode. It's like this stretching mode. So this one will go like this. It's a stretching mode. So in this whole process, you can see that the Raman tensor is something like this. And then this one will just get bigger. So remember, drawing is not very accurate. It's an ellipsoid, okay? It's an ellipsoid. Okay, so this one is Raman active. So what about the mole? If you get the mole, this will be hydrogen is small, so hydrogen will get more electron. So you have this negative sign here, negative, positive. So the dipole is like going up, and now the whole thing gets smaller, right? So the dipole will be small, smaller p, and then larger p, so get bigger. So from here, you can already see that this is Raman active, because this small, big, small, So if you plot the Raman tensor, you will see that it go like this. Okay, so the slope is not zero. Okay, so this one is oscillating. You can see this oscillating. So it is also infrared active. So also IR active. So for water molecule with the lower symmetry, both modes are this mode is both Raman active and infrared active. Is okay? Okay, so let's do one more. There are also 3 vibrational modes, and they're actually very similar. Another one is this bending mode. Let me make it bigger. Like it doesn't. Okay, so this bend like this, and then so it's just this bending mode, like flying. Okay. So similarly, we copy this. And then when it bends more, it will behave more like a sphere. So let me just draw a sphere. And it may not be a sphere. Draw something like a sphere, okay? And then this one will be more asymmetric. Okay, so these are different. Okay, if you plot the Raman tensor, it will also go like this. Okay, the slope is also non-zero. Okay, so this mode is Raman active. And similarly, you just draw the dipole. So this will be a bigger dipole. This will be a smaller dipole. This will be even smaller. So also infrared active. Okay, let's do one more, then we're done. Okay, so another one is this mode. Okay, this is the mode that corresponds to the one in I mean in CO2 you have 3. Here you also have 3. Okay, if you draw the ellipsoid, this one will be just the original one. Okay, this is the original one. And this one, you can see that it is tilted. It is tilted. So if you draw the ellipsoid, it will look like this. It will be something like this. Maybe it doesn't tilt this much. Okay. And then if you go to the other one, it will go like something like this. Is it? Okay. So here you can see that probably the form doesn't change too much, but the orientation changes. Okay, because it distorts the molecule. Okay, so if you plot alpha as a function of Q, you will also see a slope. Okay, so it's positive. Okay, so that's why this one is also Raman active. Okay, now let's consider the dipole. Something similar. So you have positive dipole, and then here certainly the dipole already tilted. Okay, you have some charges here and here. So if you measure the dipole, there will be something like tilted. Okay, so here is the same. So you will see a dipole like this. Okay, so the dipole is going like this. It's also a changing dipole. So this one is also infrared active. Okay, so in summary, let me get the summary thing first. Okay. If you do the summary for water, then all of them will be yes. Okay, so that's the difference. So you can see that the main reason all of them are active is because water has a lower symmetry. Okay, so from this you can see the relationship between them. Okay, any questions before we move on?
Explain the infrared active.
The infrared active is when the dipole is changing. Okay, so okay, let's consider the emission of light. How can you emit the light? If you have a charge there, how do you emit the light? You emit the light by applying acceleration to the charge, right? Okay. The only way to maybe if you have a charge, okay, let's say electron here. How do you make the electron emit light? You make it accelerate. Accelerating charge will produce light. Okay, so and the typical way is to make the electron oscillate. Okay, if the electron oscillates like this, if the electron oscillate like this, as a function of time, then the oscillating charge will produce light. And the oscillating charge produces light. Okay. So how do you express an oscillating charge? You use the dipole. I mean, because once you fix the origin here, then you have an electron. Then this is the D. Then the dipole is just D times the charge. Then you have a dipole. Okay, when this D is changing, then it just produce the light.
Yeah, but why is it called infrared?
Because the frequency. Because the phonon frequency, when you convert it into wavelength, is in the infrared range. Is that your question?
Mm-hmm.
So Raman and infrared always come together because they have similar energy scale. They're mainly in the mid-infrared, like a few micron, 10 micron, 20 micron. Yeah. So just because energy consideration. Any other questions? Okay. So now let's come to more related to 2D materials. Okay, I want to show you how we can apply this to our research. I actually have a paper on that. Okay, so this paper is the one that I published in 2015. Okay, so I was a postdoc at that time. So I got this paper on applied physics letter. So this paper is pretty simple. Pretty simple. So you don't need a very difficult physics to publish a paper, but it's simple. It's also quite elegant. That is on the stacking dependent shear mode in trilayer graphene. So let me introduce what the shear mode is. Okay, so this is two kind of a trilayer graphene. You have a single layer graphene here. Okay, is a hexagonal. A lot of hexagons come together to form a honeycomb lattice. Then they stack together, they form ABA. So you can you look here. This A atom corresponds to the B atom and correspond to A atom in the third layer. So that's why it's called ABA. Okay. So if you go to the ABC, you look at here. C means the center. Okay, A. Let's say this A correspond to B atom. And the B, and if you go continue down here, the B atom is on the center of this hexagon in the third layer. Okay, and we call this the position C. Okay, so this B is on top of C. So that's why it's called A, B, C, ABC stacking. So when you have these two kind of stacking, they have actually different symmetry. This is a D3H. This is, sorry, I just highlight the whole thing. Sorry, D3H. This is D3D. They are of symmetry, different symmetry groups. Okay, different symmetry. If you see the phonon band structure of AB and ABC, they look almost the same. If you just look at the energy. So these are two acoustic mode. And this C and C prime are the two interlayer mode. The two interlayer mode. These also have two interlayer mode. Then let's look at what they mean. Okay, so this lower frequency one, you see there's a lower frequency one and a higher frequency one. This is one mode, this is another mode. So this corresponds to the shear mode. Okay, so you have three layers. If this layer stay the same, this layer move on one side, this layer move on the other side, then they form the shear vibration. Is that okay? Okay. Then you go to a higher shear mode. If the middle one also move, like both the top and bottom layer move in one direction, the middle one move in opposite direction, that's another shear mode. Okay, like this. Okay, and it is higher frequency because there's more distortion on the interlayer bond. Okay, this layer and this layer, they're connected by some weak bonds. It's weak, but it's a certain bond. So when you distort the bond, you produce, you cause some energy. So this is why the lower shear mode, the higher shear mode, you have exactly the same thing in ABC. You have exactly the same thing on ABC. So that's why here I did not know what kind of stacking is, because you just do the same for two kind of trilayer. Okay, this is the breathing mode. The breathing mode is almost the same as the shear mode, but except that the direction is different. For this mode, the middle layer is the same. The two layers just go up. Okay. You can just imagine this as the carbon dioxide atom, a molecule. Okay, so for here, I have this. Let me see. So I have this carbon dioxide thing. Okay. Okay, this is one mole. This is one mole. In this mole, this one go one direction and the other go in the opposite direction. And in this mole, these two just go this and this doesn't move. Okay, so it is just the same as a carbon dioxide. Carbon dioxide. Okay, so the same for both the shear mode and layer breathing mode, they're just on different direction. And this one stretch the bond more, so it's of a high energy. So you see these two here. Okay, these two. Layer breathing mode, high and low. Okay, so if you look at the phonon band structure, the energies are almost quite similar. Okay, so what is the physics there? However, if you measure the Raman, okay, this is the Raman spectrum of ABA and ABC trilayer graphene. You see that they only show one layer breathing mode for both layers. You're supposed to have two layer breathing mode, but when you measure the Raman, you only see one. You only see one. And when you measure the shear mode, you see one for ABA, you see another one on ABC, and you see that they appear at different energy. That means for ABA, we're seeing the higher energy shear mode. For ABC, we're seeing the lower energy shear mode. Okay, so how do we explain this? Okay, that is the experimental data. And how do we explain it? Okay. So we explain it by using the physics that I just told you. You just draw out the cartoon. You explain it. Okay. Okay, so I actually draw it out in the paper. Okay, so let's learn that. Okay, let's learn that. Okay, so I don't bother to draw it again. Let's just look at. Okay, this big Q is the displacement vector, the displacement for the normal mode. Okay, let's look at ABA. ABA I think this one is the higher energy mode. Okay, ABA, the high energy shear mode. Let's look at the shear mode first. So this is the figure that I simplify. So you have the top layer, you have the bottom layer, middle layer, you have A correspond to B, correspond to A. Okay, so how do you get this one? You look at here. Where should I start? Okay, you look at the middle one, A. Draw it down, you have a B. You draw it down, you have another A. So you draw this one, and you draw from here, you go to another one. And from here, you go to another one. So you draw this 1, 2, 3, 4. And with this one, then you get what I got. Okay. So this is the one that I outlined for you. Okay, so now let's consider the oscillation. Okay, the first mode, the high energy mode is this one. Okay, this one move on one side, this one move on the other side. Okay, so once you move, you can see that when Q is larger than 0, this move on one side, this move on the other side. And when this move on the other side, then you have something like a zigzag oscillation. Is it clear? Okay, so now let me ask you, is this Raman active or not? Yes? No? Okay, then let's just draw. If you draw the Raman tensor out, okay, one is this. The other is this. One is this. Okay, if you draw the Raman tensor out, this is longer, right? So you expect something like this. Then this is more symmetric. You expect something like this. Okay, if you plot it out, then it will be something like this. So it is Raman active. Is it okay? Not too difficult to understand. Is it okay?
I think it's more symmetric. Longer.
You just treat it as a molecule. You just treat it as a molecule.
So the left one is more symmetric.
Not more symmetric, it's just different.
More compact.
Yeah, more compact. And actually, whether it's compact or long, it doesn't matter. What matters is that this one is not the same as this. Okay, as long as they're not the same, you get the slope. Like this is a certain value, this is a higher value, this is a lower value. When you plot it, there will be a slope. That is one matter. Of course, okay, if you say this is longer, this is wider, then you just draw in another way. Then you get another slope. But no matter what, the slope is not going to be 0. Okay, so this is one matter. I mean, maybe I make a mistake. This is not smaller, not bigger, but it doesn't matter. As long as the two ends are not the same, you will get a finite slope. Is it okay? So this one is finite Raman. Okay, finite Raman. Okay, now look at the ABC, exactly the same mode. Exactly the same mode. So this one is going to move in one direction. This one is going to move another. Let me just draw it out then. Okay, let me just draw it out. So this is going to move like this. Okay, so if you move, it will be set like this, and then it will be like this. Is it? Yeah, like this. Okay, because this one is moving one, then you just follow this direction. You just follow this direction. Then if they go to the opposite way, then you're gonna have this. Gonna have something like this. Sorry, you're gonna have something like this. You draw it like this, then you're gonna have something like this. But drawing is not very accurate. But that is the result. Okay, you look at this one, and you look at this one. Do they look the same? Yeah. Okay, but when you shine the light, with XY polarization, the light is going to pass through. The induced polarization will not differentiate what is top or bottom. It will not be able to differentiate what is top or bottom. If you shine a horizontal polarization light, polarized light, they will induce exactly the same dipole as this one. Okay, is that okay? So this two will produce the same polarizability. So when you plot it out, the middle one will be flat. Okay, so this one is 0 Raman. Is that okay? Okay, now let's go to the lower energy mode. The lower energy one. Okay, what is the lower energy one? The lower energy one is this. Is this one. The middle layer does not move. The top and bottom layer moving opposite side. Moving opposite side. Okay, so let's see how it does this. Let me just draw it then. I think that would be easier to visualize it. Okay, so this one will move in one side. So eventually, you get this. Okay, this is Q smaller than 0. Then Q bigger than 0 will be the opposite. Yeah, will be the opposite. Okay. Then you look at here, this one and this one, they just look the same. Okay, what is tilted this way or tilted this way, it doesn't matter. It's not like in water molecule, because here you have repetition of a lot of units. It's just only one unit cell, but in reality, you have repetition of many of them. Okay, if you shine the electric field here, they will just produce just the same dipole. They will just produce the same dipole. Is that okay? So this two and this two have the same polarizability. So this two eventually it will give you 0 Raman. 0 Raman. And particularly here, we're considering when the electric field is on the XY plane. And this is our geometry in experiment. Okay.
It's out of plane.
Yeah, you just the normal one that you use here. You shine the light vertically, then the electric will be in plane. And the in plane electric field won't be able to differentiate this kind of which way they're tilted.
So it means that if you shine the light, you're going to see the bump.
I don't think there's a difference either. Yeah.
Oh, not for this one.
Yeah, I don't think there will be a difference either. It actually matters. It actually matters. But let's keep it simple for now. Just consider in plane electric field. Suppose you are the electric field. When you induce a polarization, it just induce a dipole, they will just be the same. Okay, so let's keep it simple. Okay, so this one has 0 Raman. Okay, let's go to look at this one. Okay, let me draw it again. You have this, this. So this will go this way. This will go this way. So if you go this way, then you have this. You just stretch it. But when you go to the other way, when you go this way, then Then this one will be like this. Okay, so certainly this one and this one, they look different, right? So if you plot the Raman tensor, you're going to see if you plot the polarizability tensor, you're going to see a slope. You're going to see something like this. Okay, so this is Raman finite. So from here you can see ABA and ABC, they have opposite Raman activity. This is finite, 0. This is 0 and finite. So that explains our data. Why in ABA you see the higher mode, not the lower mode. In ABC you don't see the higher mode, you see the lower mode. So that explains it. Just some cartoon, you understand it. Of course, we also have the group theory analysis. I have the representation here. You can actually see ABA and ABC. For ABA, actually, both of them are Raman active. However, the direction of the electric field will make a difference because we're considering XY polarization. For XY polarization, this is Raman active, this is not. Okay, the lower one is not because you in the in plane you don't see it. That's why when you draw the cartoon, you visualize it. Okay, you visualize it. Okay, so now let's go to the breathing mode. Why is the breathing mode are exactly the same for both? Okay, then you just draw the same cartoon. This is figure 3 is a cartoon. Figure 4 is another cartoon. Okay, so probably this is the paper that you see. A lot of simple cartoons. Okay, so it's a kind of an interesting paper in this perspective. Okay, so let's look at the breathing mode is much simpler. Let's look at the vibration. So in the higher vibration, the middle one will go down and both of the layer will move in opposite direction. Okay, so on one end, you have this. You have this, okay? You have this. So if you shine in plane light, this one and this one, they just look exactly the same, right? If you shine in plane light, like in plane polarization of the light, this one and this one will produce just the same XY dipole. Okay, so these two will have the same polarizability. So when you do the derivative, you'll get a flat. You get something flat. Is that okay? And then when you look at ABC, you just get the same thing as well. Okay, you just
also 0.
They're both 0. It doesn't matter about stacking now. It doesn't matter about stacking. Both of them are 0. You just treat them like a CO2 atom. Sorry, CO2 molecule. They just behave just like a CO2 molecule in the vertical way. Okay. So, okay, when you look at the lower one is the middle one doesn't move. The top and the bottom layer just go up and down, like a stretching mode, And you can see that this one is more compact. This one is more stretched out. Then this one and this one will have a different polarizability tensor. So when you do the derivative, you get a finite value, right? So this one is Raman active. When you go to here, you just get exactly the same thing, basically. This is more stretching out. This is more compact. When you do the derivative, you get the finite Raman. Okay, so that means for breathing mode, you don't have any difference between them. Both of them are Raman active. And for the higher one, both of them are Raman inactive. So that's why in the experiment, you see this Raman mode here. And the higher one, not there. From the experiment, they look just the same. Okay. Very small difference because the interlayer bond, the strength, does not depend on the stacking. So generally, the layer breathing mode is just the same. When you look at the shear mode, the amplitude is different. And actually, in the paper, we explained that we have this polarizability bonding model that we are able to get the magnitude. is square root 2, square root 6. We can kind of approximately explain the intensity difference. So what I'm showing you is a very qualitative model. I just draw a cartoon, show it is 0 or not 0. It's very qualitative. And you can actually put it in a more quantitative analysis. This is what we did in this paper. We actually build upon these cartoons. We have a more quantitative calculation. We can actually get the ratio, like 0, square root 6, square root 2, 0. So we actually get something, okay. And eventually, of course, we need to consider other factors altogether. We get the ratio that is about 1/2, and actually that agree pretty well with our experiment. Okay. So let me draw you to the attention of another paper. This one. Okay. So this is a Jeremiah's paper. Okay, called the Stacking Dependent Interlayer Phonons in 3R and 2H MOS2. Okay, that is both paper. The measurement was done in Professor Rui's lab, and we analyzed the data. Because the measurement is actually pretty simple. You make the sample, one stacking, another stacking. You measure the Raman. That's it. Okay. The measurement, I think, for this paper, the measurement was done by the undergrad. Yeah. So you even undergrad can publish a paper if they know the physics. Okay. Like the physics that I told you is understandable for undergrad. Probably even high school student, they probably if there's some good student in high school, they can probably understand. Yeah, so you can see that in this paper, we only show one set of data here. It's very simple. So that means when you do research, one method is really the idea. Some of the experiment can be quite simple. Okay, so let me see. This is Jeremiah's paper. Let me show you the data. So this is 3R MOS2, 2H MOS2. This is a parallel polarization. This is horizontal, and this is cross polarized. That means you excite it in one polarization and collect it with the vertical polarization. So you can see that they have different results. They have different results. So we actually build a model to explain it. Okay, so you see this cartoon again? Okay, so I like using this kind of cartoon. Okay, so this is on a trilayer MOS2, 3R and 2H. So you have this displacement. Okay, this is a 3R. If you do a vibrational mode like this, so you can see. Can someone tell whether this is Raman active or not? Not? Really? Really? I already write it here. Yeah, it's not. Okay, it's not. Okay. Okay, good. Okay, good. Definitely good observation. It's not. Okay, yeah, it is not. Okay. So when you go to 2H, okay, when you go to the 2H, we draw the stacking here. Then you can see these two are different, right? So you have Raman active. Okay. So this is a lower mode. I mean, we already draw it out. So when you look at here, you can already know because they look different. When they look different, they're different. Okay, so this is Raman active, and this two and this two, they look the same. Okay, so that is what we observe. Okay, for 2H, you see higher mode. So 3R, you see the lower mode. Okay, and we actually build a quantitative model to do the calculation. Okay. So this is like a very simple example in 3-layer. Then later we build a quantitative model, which we won't go through the quantitative model in this lecture, but basically you can see that for 3R and 2H, the polarizability tensor, they're going to have opposite sign because because the bond direction is different. Okay, so if you're interested, you can read this paper. So let me show you more of this cartoon. When you go to a higher layer number, we put in the supplementary material. Okay. This is a quite comprehensive paper just on this particular topic. Okay, a lot of analysis. These are the group theory results. Okay, but I mean, I separated this Raman active, infrared active. So we separate the mode for different modes. Okay, for different modes. Okay, so this is another one. Okay, this is for 5 layer. Okay, for 5 layer. So you have 5 modes. You have 5 modes. So let's briefly go through it. It's just the same thing, just on a higher layer number. Okay. So for the first mode, okay, so you have this one go up, go down, and this two have this arrow represent the vibration magnitude. Basically, it corresponds to like you have an oscillating string. You have more and more oscillation. And this two, you can see this two just look the same. With the bigger than 0, smaller than 0, you invert it, it just look the same. So this is not Raman active. But for the 2H, you do the same, exactly the same displacement. You get this one and this one. They look different. So this is Raman active. You go to another mode. You go to another branch of the breathing, the shear mode. Then these two will look different. You need to pay attention. Okay, why they look different? You need to compare this and this. They are actually different. Okay, and when you go to the 2H, then they look the same. They look the same. So this is not Raman active. Then when you go down to another one, this two, this one and this one just look the same. You invert the layer, they just look the same. And this one will look different. Okay. And similarly, you go to here, this is not the same. These are the same. Okay. So I think Jeremiah spent quite some time to make these figures. Okay. And then eventually, this is the result. If you combine the 2H and 3R, you see 1, 2, 3, 4. So these are the 4 shear mode. You can see they're always complementary. You have one, then the other one don't have. Okay, so they're complementary, and we can actually do the calculation. Even the relative magnitude between them can be kind of roughly calculated. So we can actually kind of simulate this data using a simple quantitative model based on this cartoon. Okay, so yeah, more or less, if you go to higher layer number, then you can have something similar. Okay, are there any more cartoon? No more. Okay, I think that the best one we got is 5 layer. We draw the cartoon is 5 layer. Okay, so this is another example. If you're interested, you can read this paper, and you can read this paper. I think that would be a kind of a good education for you to learn this topic. So the Raman can just use the simple cartoon to have a good understanding of the results. Any questions? Okay, if no, then we just end the lecture here. Thank you very much.